This time, we have a rusted out old junker, egg protein, and a whole lot of fireflies. We are going to use them to learn about the rates of chemical reactions and how those rates help keep the economy running. Should be fun. If you reflect on it a little bit, you will realize that huge sections of the economy depend delicately on how fast chemical reactions happen. One good example is the rusting of iron, the chemical reaction by which iron reacts with oxygen to form iron oxide. The overall reaction is shown here. What does it matter how fast that reaction happens? Think about the automobile industry. Cars are largely constructed of steel, an alloy containing principally iron. Steel also contains a small percent weight of carbon and sometimes traces of other metals. Over its lifetime, a car is exposed to the atmosphere, which contains an appreciable quantity of oxygen and other sources of oxygen, such as rainwater and so forth. The iron-containing parts in the car react with that oxygen, forming iron oxide, aka rust. Rust is not good for making car parts. It's a crumbly powder. So why is it that we can make use of iron so extensively in vehicle construction? Because the reaction by which iron turns to rust is slow. Under typical conditions, an automobile will last at least 10 years before the formation of rust becomes a prohibitive problem. What would happen if the reaction were 10 times faster? A typical car would become rusted junk in a year. The automobile industry, of course, would love to sell us each a new car every year, but very few of us would be willing to pay current prices. The industry would have to dramatically drop the price of a new car. That's probably not possible given manufacturing costs. Now suppose the above reaction were 10 times slower. In that case, once we purchased a car, we would almost never need a new one, unless we were in a wreck or wanted some new features. The automobile industry wouldn't generate sufficient sales to continue. It seems the entire existence of the automobile industry depends on the rate at which iron rusts. Chemists call the study of the rate of chemical reactions chemical kinetics. If you want a chemical reaction to go faster, often a very efficient way to accomplish that is to raise the temperature. You almost certainly make use of this fact regularly without even thinking about it. When you cook, consider frying an egg, for example. Chemically, cooking an egg is carrying out a chemical reaction whereby the proteins in native form become denatured. Here, OVA stands for ovalbumin, the principal protein in egg white. This reaction is basically a conformational change in the protein, and it is favored at high temperature. See the Quarantine Chem Lab on thermochemistry for more about that. More importantly for the present study, not only does high temperature favor product, the higher the temperature of the stove burner, the faster the egg will cook. Of course, attempts to cook the egg too fast lead to undesirable side products like charcoal. So when cooking, one needs to find an optimum between getting the egg cooked swiftly and not burning it. There is actually a quantitative analytic relationship that expresses how temperature influences the rate of a chemical reaction. This experiment explores that relationship. How are we going to do that without any laboratory chemicals or labware? By observing fireflies, also known as lightning bugs. No, our biologist colleagues would almost certainly point out that fireflies are not flies, they are beetles. Fireflies produce light by an enzyme-catalyzed chemiluminescence reaction. Every time they flash, they must produce reactants again to recharge for the next flash. We can use the interval between flashes as a metric of the rate of these chemical reactions. Actually, we need the reciprocal of this interval. More on that in a minute. By observing the flashing rate at different temperatures, which can be achieved by observing across different days or times of day, we can investigate the temperature dependence of the rate. Here is the math behind what we are doing. It's mostly just algebra of the kind expected by AP. It will also help to know what a derivative is, a concept from first semester calculus, but that's not essential. Of course, you can always return here later if you missed something. Consider a generic unimolecular reaction in which reactants R are converted to products P. The rate, which we will denote lowercase r, is defined as the time derivative of the concentration of a reactant or product. Typically, it may be expressed mathematically by the product of a rate constant, K, and the concentrations of the reactant species, R. If we know the rate constant, then knowledge of the reactant concentration yields the reaction rate. A key point for the present experiment is that the constant of proportionality K isn't really a constant at all. It's only constant at a fixed temperature. In general, the temperature dependence of the rate constant can be expressed with the Arrhenius equation. Here, Z is termed the pre-exponential factor or frequency factor. EACT is the activation energy for the reaction, R is the gas law constant, and T is Kelvin temperature. The Arrhenius equation expresses the rate constant as a product of two factors. Z is the rate at which the system attempts to react. The physical interpretation of Z depends on the mechanism of the reaction. For example, this could be a frequency with which two reactant species collide, or a vibrational frequency with which a chemical bond stretches. The exponential factor is a unitless quantity that gives the probability that the reaction will successfully reach product when it is attempted. If we define a constant A to be the product of Z and the concentration, by substitution, we obtain this expression. Taking the log of both sides and writing 1 over t as the independent variable, we obtain a linear form. We say linear because this form may be thought of as y equals m times x plus b. The key feature for the present experiment is that if we plot the log of the rate versus 1 over temperature, we will obtain a straight line, the slope of which is equal to minus the activation energy over r. Multiplying the slope by minus r, therefore, yields the activation energy. Very conveniently, the concentration R is never needed to find the activation energy.
In this experiment, you will need a timing device. One with the lap feature will be helpful. A computer with spreadsheet software. A place to observe fireflies. And we also recommend bug spray.
The goal of the experimental procedure is to determine the rate at which fireflies flash for a range of temperatures. There are a couple of ways to obtain the rate. A good strategy is to observe fireflies after sunset, but before it becomes completely dark, so you can see the fireflies even when they aren't lit. Using a stopwatch, if you start the watch on the first flash, and stop the watch on the nth flash, the average period between flashes is the total elapsed time divided by n minus 1. The caveat to this is that they need to be regularly spaced flashes. At some point, the firefly will quit flashing or take a long break from flashing, and that will spoil your data taking. So keep the data from cases where you track several more or less regularly spaced flashes. Another point, apparently the male fireflies fly around generally about 1 meter above the ground, flashing. The females hang out on the ground, often in the grass, watching. When they see a male they like, they flash to attract it. I don't know if male and female fireflies flash at different rates. The males seem to flash a lot more, So despite the fact that they're moving around and harder to track, we got data mostly for flying, presumably male, fireflies. If you have a stopwatch with a lap timer feature, most phone stopwatch apps do, this is especially useful because you can click the lap timer on each flash and you don't have to worry that the firefly will decide to stop flashing entirely and spoil your data taking. Just record several regularly spaced flashes and take the average lap time. If you find it difficult to track the fireflies for multiple flashes, an alternative strategy is to simply time the duration from one flash to the next. By doing so for numerous fireflies, you should be able to establish a good average period. Regardless of how you obtain the period between flashes, you also need to record the ambient temperature. You can use the thermometer or get the temperature from the local weather service. Since there's some local variation in temperature, obviously having a thermometer exactly where you observe the fireflies is the most accurate. If you want to perform the experiment at a time and place when fireflies are not active, there are a couple of options. It turns out that the chirping of crickets obeys similar kinetics, so you can time the duration between cricket chirps and record that for a range of temperatures. Folklore has it that the temperature dependence of cricket chirping is so consistent that it can be used to determine the temperature with some accuracy. To determine the temperature in degrees F, add 37 to the number of chirps in a 15-second period. Another source suggests that adding 40 to the number of chirps in 14 seconds gives the temperature in degrees F. You could even use one of these empirical formulas to make some fake data for crickets. For the scenario where neither fireflies nor crickets are available, and because you're a fine scholar and don't want to make up fake data, we will show some video and place more video on our website so you can observe fireflies, at least virtually, and take your own data. Here are 3 short clips of fireflies flashing. Here is our data for June 25th. I recorded the interval between flashes and took the average. Here's our data for June 26th, June 27th, and so forth. I took the data for numerous days. I recorded the temperature for each day, which I converted to degrees K, and then to reciprocal temperature. In column F, I recorded the average duration between flashes for each day. In column G, I computed the reciprocal of the duration, which is the rate. In column H, I computed the log of the rate. If you remember this equation, it shows that if we plot the log of the rate versus 1 over temperature, we will obtain a straight line, the slope of which is equal to minus the activation energy over R. Multiplying the slope by minus R, therefore, yields the activation energy. You can obtain the slope directly from the plot using the trend line tool. But it's usually more accurate to use the regression function, which I've done in cell I2. Cell L2 contains the gas law constant in joules per K mole. Cell L5 multiplies the slope by minus R, which yields the molar activation energy. Cell L3 contains the Avogadro number. Cell L6 divides cell L5 by the Avogadro number, giving the final number we seek, 7.74 times 10 to the minus 20 joules per firefly. Your final task is to interpret the results. Do they make physical sense? Try this comparison. Look up the activation energy for the combustion of methane. It will probably be given per mole, so convert to per molecule. How does it compare to the activation energy you found for the firefly kinetics? Are they similar in magnitude? Which one is larger? Does that make sense? Pause the video here so you can do the calculation yourself before comparing answers. Now that you are back, here is the comparison. A quick web search turned up the value 64 kilocalories per mole for the activation energy for the combustion of methane. Since there are 4,184 joules per kilocalorie and 6.023 times 10 to the 23rd particles per mole, that converts to 4.4 times 10 to the minus 19 joules per methane molecule. By comparison, that's significantly larger than the firefly flashing activation energy. This seems to be a plausible result. Methane does not spontaneously catch fire at temperatures where fireflies are active. The reaction required for a firefly to flash is considerably easier to get started than burning of methane. It turns out that a very similar firefly experiment was actually carried out by some individuals at the Johns Hopkins University and published in 1920. You can look up the article and compare data. See if your flashing periods are similar. What do you suppose might account for any differences?